Yeah. Okay. It's recording. Yeah. Yeah. Thanks for the reminder. Okay. So this is so here's where we are. And so hopefully by Friday, and if not, even if you don't have your board soldered together, that's okay. Come in Friday with your kit and we'll help you get your board soldered together. You can also come in tomorrow at 2 and you can solder now in the DSD lab, same room at 2 p.m. We'll be there for several hours. I'll probably be there for an hour or so. And we'll break out one of the soldering kits. You can solder up your board. If you do find you're missing a part, no big deal. Just come in and get it. And you can come in tomorrow at 2 and get it and solder it on or whatever. And Friday, if you don't have it done, come in, bring your kit. We'll have you solder Friday and then you can do your lab. So I'd like everybody to get their board soldered by Friday and at least get started, see if they can get started on the first lab and hopefully get it done. It's not that long. But the first one's kind of awkward because you're learning everything brand new. The IDE, the board, the instruction set, it is a lot. That's what I'm going to go over today. Okay, so if you go in the website, so here's the website, and remember this is the office hours link. It's not the link for the lecture. And here's the syllabus, and
it's your screen.
Oh, that's right. Sorry. So here's what it looks. This is the office hours, which I'll do at noon on Mondays, or 12:10 actually. And anybody's welcome. Once we get past the COVID stuff, I'll probably be in my office to do that. So you can come in physically or you can come in on Zoom. All right, syllabus is here. And then these others you can't see, but here's the lab folder. So if we click on and here are the lecture videos, again, you can look at them if you want. You can try the quizzes if you want. Unlimited attempts are all turned on, but they don't count. So don't worry about them. And the other thing is, here's the prereq quiz. Some people said they couldn't find the prereq quiz. I don't know why. It's right there. It's got 3 different portions. So click that folder, do the first one, do the second one, do the third one. There's only, I think, 4 questions each, so it won't take you long to do all 3 of them. I broke them out like that because they're automatically graded, and when it's all done, I have 3 grades for the 3 parts that I need to do the analysis on, so I don't have to break out the grades and screw around with it. It's all done for me automatically, which is really nice. So do the prereq quiz. Everybody should get it done this week. And then I'll do my little analysis, which is basically for ABET purposes, but it does guide me a little bit. But I know most of you, it's the typical case that most of you don't have a good grasp on programming. Although I know those of you who took Bob Aballone's course and not the CS course probably do have a much better grasp. And so hopefully we'll start to really see some differences this semester with people with a much better grasp of C. And we're going to get into C. But before we do that, we're going to learn how this chip works. And that's why we're learning assembly language. Okay, so in the lab folder, here it is. And mine looks a little different than yours because there's a few things showing up that maybe, well, it looks about the same. So here you have a zipped PuTTY file, which you can download, and then you can unzip it and you can run it. So that's the terminal program. You can also just download it, but this, you can't put an executable on here, but you can put an executable in a zipped file. So that's how we did it. Here's the latest pinout for the board, and it shows you all the various connections and everything. And then this will get you to the archive. So if you go to this brings up the Microchip website, and these are the archives. And what's really amazing is Microchip makes every single integrated development environment they ever published, all the versions, available from their very, very first one to the most recent one. Now, there's a little bit of a problem. And you can see these are MPLAB IDEs, but they're not MPLAB X. MPLAB X, and this is for Windows, Mac, Linux. So that's the very first version of MPLAB. And let's see. Oh, these are MPLAB X, MPLAB IDE X. This is MPLAB IDE. So these are different. This was the old one, and this is the new one. And if you go through here, These are all of the XC8 compiler versions from version 1 to all the way up. Now, there's several considerations, and the main consideration is that I want you to do I want you to use certain versions, and there's a bunch of pages here. There's a lot of these, so don't do any of these. Go all the way. If you go to the last page here, you're up to version 5.15, 5.2, 5.3, 5.35, 5.4, and 5.45. I can't remember right where it is, but somewhere in here, maybe version 5.40 or 5.45, they took out a direct access to the assembler. Of course, it's still there, because once you compile C, you compile it into assembler, and then you have to assemble the assembler into machine language and then load it. So the assembler is still there, but they just made it so it's very hard to get at it, to use it directly. And why they did that's beyond me. I'm still trying to comprehend that. But because they have some chips out there that require assembly language, because there's not enough memory to do C in them. And there are people still using those chips and writing code for them. But anyway, we're only doing this to really give you insight into how the code works, how the processor works. But it's I think a very useful exercise. So I'm currently, the one I'm using on my computer right now is 5.20. I think you can do 5.3 or 5.35. I think that's fine. I'm not sure about 5.40. I can't remember. I have that loaded up. I can check it. But so probably 5.20 is the best one to do, or 5.30 or 5.35. But don't do the latest one, because that one will not support assembly language directly. I think there's a way to do it. And then make sure Windows, Mac, Linux. So get the one you need. You probably need Windows, 64-bit version. Okay, down here in the C compiler, down here, this is XC. This is XC. No, that's for the next one. So this is XC8, I think, right? Yeah, XC8. So that's the compiler we're using, and we could use the latest version of this one as well. But they changed the way the directory structure works. I'll probably go to this maybe next semester, but for this semester, go ahead and just stick with 1.45 for Windows, 1.45. You'll have a few less headaches if you do this. After 1.45, version 2.0 forces you to use the next upgrade to Windows, to C rather, and it causes a few problems. But it's not that big a deal. I mean, if you do use it, it should work. Just just be advised. I'm recommending 1.45s, and that'll keep you out of trouble. Okay, so that's what you need to load up. You have to first load the IDE, then download XC8, and then you just execute XC8. It automatically gets plugged into the Windows platform. And there's a couple other things I may have you add later on, but not yet. Okay, so that's that. So let me get rid of that and go back to here. Okay, so and that link is right here. Okay, and if you want to see about the Viva board, you can pull this up. That tells you what pins things are connected to and stuff. All right, this is just build your board, and there's some files here that'll help you a little bit. There's a little movie for the battery clip. If you don't have it done, there's an assembly guide and some other things. And some of these we've updated a little bit. Some of them may be slightly out of date, but they all are useful. All right, lab 1. This is the lab for this week. And here's the guide. There is a little turn-in sheet at the end, and you just click this link and you can turn this in. It's currently set due January 30th, 2021. I know that. I will fix it by Friday. So you don't have to, well, you might have to remind me, but I don't think I'll forget to do this. Anyway, so we'll change this due date to, we'll probably set it for this Saturday, but it doesn't matter. You can turn these in late. It doesn't matter. It's fine. There will be a date on the syllabus after which you cannot turn any more lab sheets, and you cannot do any more demos. And so if you don't have lab done, you're just in trouble. But that's coming up in November. I think it's maybe even right before, maybe it's, I think it's right the Friday before Black Friday in November, before Thanksgiving, the week before Thanksgiving, something like that. All right. Okay. Oh, I meant to go to the lab. Sorry. Screw that up. Okay. So I'm going to go through this guide. I think I have it pulled up here. Yeah, I do. Okay. So we'll go to that. So if you click on this, this brings up this PDF, and I have to update. I've made a few changes to the PDF even this semester. I'll update it. This is the old one, and I have changed it a little bit. So don't download this one till Friday. I'll fix it probably tonight or tomorrow, for sure by Thursday, so that when you do it Friday, it'll be the updated one. Okay, and there's obviously lab 2, 3, 4, 5, 6, 7, 8, 9, and then 10. This one's hidden. And there's a few other things, but okay. So, and here's the data sheet too, by the way, right here. So you should have that. And here's, oh, I guess I took that down. Okay, so you can download it from the web. You can always search for it, Google it, but and then this should, I want to download it. All right, and it's best to look at it in the viewer because you get a better thing here. And all the assembly language instructions are in here, chapter 29, instruction set summary. And I'm going to go through some of this. If you scroll down just a little bit, you'll see all the assembly line instructions. Starts here, it's table 29.3, all that and all that. That's it. There are only 50 of them, or 49, I guess. And of all these, you're going to become familiar with a few of these: the decrement F, skip on 0, the bit clear F, bit set F, bit test F, skip clear, bit test F, skip set, and all these literal operations, or most of them, that deal with the W register. The one that deals with the programming counter latch high, you probably can skip. The one that deals with the BSR, you'll use a compiler directive and let it make this instruction for you. You won't do this directly. And the rest of them, the main one you'll use here is move literal to W. And then that just takes a literal word and puts it in W. Okay. And then there's a call subroutine and return from subroutine, call subroutine, return from subroutine, and we'll also return from interrupt, and then go to and branch always and go to. And then there's a few of these. We'll use the sleep instruction, and that's about it. Tris is a legacy one. We don't use that, and neither the no-op. You might use the no-op, but anyway. Okay. All right, so those are all the instructions, and we're going to go over those. But today we're going to just go over the ones you're going to need for Friday. Okay. Now let me see. Back to. And I'm going to kill this. Yeah. Okay. So. Okay. And for some reason, this horizontal. I don't know why. It's kind of strange. All right. Well, anyway. Okay. We'll put it here somewhere. All right. Oh, didn't work. Oh, now it went this way. Okay. All right. So back to the data sheet for today. And so for that, we'll pull up the Adobe Reader, and we'll actually pull up this one instead. All right. So here it is. I'm going to kind of go through that, but I'm also going to use some slides. So let me at this point bring up the slides, and I'm going to go through what I covered on Thursday a little more quickly. All right. So we covered some of this already, and then we're going to get into the second part. So, all right. So we talked a little bit about this. Again, my main interest in teaching you assembly languages so you can understand how this chip works. And I do want you to become familiar with the IDE. I do want you to use some of the debug features in the IDE because that's very important. You need to have a little bit of a grasp that there are debug features built into essentially every integrated development environment, or most of them. And those debug features can be very, very happy. Over the course, we're going to learn about some of the electrical parts of the board and how we can connect other things to your Viva board. So anyway, so this is the whole idea. Again, the main purpose, it does help you in debugging, even if you're just writing in C. It also helps you understand how your C instructions are implemented. It helps you understand how the chip works. It's just very powerful for a lot of reasons. Okay. So we've talked about layers of abstraction. All right. And I'm not going to go through this again. So again, this was sort of the block diagram. So remember, we have separate program memory, which has its own address and data bus. The data bus is 14 bits wide. The address bus is 15 bits wide. We have our own data memory that's also separate from the program memory. The data bus is 8 bits wide only, and the address bus is 12 bits wide. Both the program memory and the data memory can be gotten to using the indirect registers, which are 16-bit registers, which you have to load 8 bits at a time. These can let you access blocks of memory bigger than a single memory page and things like that. And when you use indirect addressing, you don't have to worry about what's in the BSR because you're not using the paging feature of the memory. You're using indirect addressing instead. And some of the special function registers that you normally can't get to, like the stack and the shadow registers, are also available indirectly through indirect addressing. But we're not going to use that. We're just going to, because it kind of just complicates the picture. We're going to use the direct addressing method, which does involve pages and the bank select register. Okay, so there is an oscillator module, and there are a whole bunch of other peripheral modules: analog to digital converter, SPI, I2C, the UART, the touch module, the capture, compare, and PWM module, potentially an op amp, although not on this chip, an LCD driver module, which we're not going to use. There's a EEPROM that's also available, this little data EEPROM. I haven't talked much about this. There are 256 bytes of electrically erasable programmable read-only memory that's not flash, and you can write each individual location and erase each individual location. You can also read and write the flash in software as well, but there you have to do, I think, eight locations at the same time. You can't erase a single location, you have to erase 8. But the EEPROM, you can erase and rewrite a single location. And this is basically used for a little bit of non-volatile storage of some variables you might want to save between power off and power on cycles. And it can be very handy. I use this on my Skittle sorter. Once I got my color identifier calibrated, then I'd save those in the EEPROM. And then when I turned it back on, I could retrieve those if I wanted by holding down a key. Or I could do new ones by holding down a key or something. Forget how I did it. Anyway, and then there's data memory, which could be up to 4 kilobytes, but on this chip, we only have 1 kilobyte. Okay. And then you have the 16-level hardware stack, which in most processors would reside in data memory, but in this one, it's a separate hardware stack, and it only has 16 levels. It can't just keep going through data memory until it runs out of memory, which does cause some limits. Namely, you can't, a subroutine cannot call itself, a function cannot call itself, because it would be easy for it to call itself more than 16 times. in some cases. And once you exceed 16 calls, including an interrupt, you've overwritten one of your return addresses, and you'll never get back, and your program's trash. Okay, so you don't want to ever do that. Here's the CPU. This is where the instructions are executed. They're pulled out of program memory and executed in a pipeline manner. There are at least 2 instructions in the pipeline at any given time. And let's see. Okay. So here are the features. We've gone through these a little bit. The programmer's model. So again, the W register is the only general purpose register in the chip. And all data operations have to go through this register. So we use this register extensively for everything. The bank select register, it only has 5 bits. That's where you get your upper 5 bits of addresses of the 12-bit address for the data memory. The lower 7 bits of that address are embedded in the instruction. So when you refer to a memory location, say called variable A, the lower 7 bits of that memory address, remember the data memory has a 12-bit address, the lower 7 bits are embedded in the instruction, the move instruction, the add instruction, whatever you're doing. And the upper 5 bits must be set correctly in the BSR when you execute that instruction. Now, that sounds like a severe constraint, and you will be doing a lot of setting the BSR. You won't do that directly. What we use is what's called a compiler directive to have the compiler automatically make that MOVLB instruction for us automatically. And so we'll do that, but we'll use that compiler directive frequently. And the advantage of that is the compiler, if all you do is you say bank cell, and then you give the name of the register or the memory location you want to load the upper 5 bits in the BSR for, and the compiler will create the right instruction to do that, so you don't have to figure it out. For instance, say you want to access, say the TRIS register. Well, you don't know what bank the TRIS register is in off the top of your head in all probability. And with the bank cell, you don't have to know. You just say bank cell TRIS A, or bank cell TRIS B, or bank cell TRIS C, because remember we have A, B, and C ports. And the assembler automatically knows what bank that register is in and makes the right bank select register, the MOVLB instruction, to take care of that for you. So that's a compiler directive, and we have a number of other compiler directives we'll use. Remember, we have a program counter. It is 15 bits because the program memory has an address bus that's 15 bits. The upper 7 bits and the lower 8 bits. The lower 8 bits can be written directly, and that's called the program counter low. The upper 7 bits have to be first written into the program counter latch high, and those 7 bits then are automatically loaded in the upper 7 bits of the program counter when you write the program counter low. So you only write the program counter low when you make sure that your program counter latch high has the correct upper 7 bits for the new 15-bit value you want to put in here. But we don't have to do this because we can just use a branch always or a go-to instruction, and then the hardware does this automatically for us. These are the two 16-bit file select registers broken down into, each one has 2 8-bit registers that you can directly write to. You can use these registers if you want. You could actually store 8-bit values in them if you wanted to. But we'll probably just ignore them. But this is what you would use if you were going to do indirect addressing. And you reference them. There's a different name you use to reference them. Okay, and then finally, there's a status register. It's got 2 other bits here that are involve timeout and power down or something. I forget, sleep or something. But these are for the Z bit, the half carry bit, and the carry bit. Remember, the half carry is when you do a math operation, and the lower nibble overflows into the higher nibble, which has to do with binary coded decimal mathematics. And so we probably won't use this either. Okay, so that's the program counter. 1 general purpose register, the bank select register, the program counter, and the status register. That's all you have to know. You don't have to worry about the indirect registers. That's it. There is one other register that's mapped to every bank in the core registers, and that's the it's the interrupt register, I think, or the I forget what it's called. But anyway, we'll deal with that separately. But that's also not something we're gonna have to mess with too much. We will a little bit. Okay, so again, we've been over all this, and this is just, again, same thing. The INTCON register is that 12th register. Okay, and we will use the INTCON register when we use interrupts, but we don't consider it part of the programmer's model. Okay, all right, so here's the programmer's model: PCL, PLAT, status, BSR, and W register, of which we really just care about the bottom three. And the indirect, if you were using the indirect registers, you reference them with FSR0, FSR0, FSR0L, FSR0H, FSR1L, FSR1H, and then, but when you actually use them in an instruction, you use the name INDF0 and INDF1 to refer to the whole 16 bits. And that allows you in the instruction to essentially reference 16 bits, even though it is an 8-bit processor. So kind of interesting. All right. So we have 32 banks, and you can see all these banks if you go into the data sheet right here, and you go all the way back here near the beginning where it says memory organization, chapter 3. And if we go to that and we scroll down, it tells you about the stack. It tells you about a bunch of different stuff. It tells you about the core registers here. And then finally tells you about the status register. Remember the Z bit, the digit carry bit, and the carry bit, and also the timeout and power down bits. But here it talks about the memory banks, and every memory bank set up like this. The first 12 bytes are core registers mapped to every bank. The next 20 are special function registers not mapped to every bank, so they're bank specific. The next are 80 general purpose random access memory locations, not mapped to every bank, they're bank specific. So, and then finally, the last 16 bytes of random access memory, those that actually appear in the first bank, bank 0, are mapped to every bank so that you can put your variables in these RAM locations, and you don't have to worry about changing the BSR to correctly access them. And then we actually have all the banks listed here. Bank 0 through bank 7, 8 through 15, 16 through 23, 24 through 31. And you can see the last bank that has random access memory in it is bank 12. And in it only 48 bytes. And all the other earlier banks have 80, 80, 80, 80, 80, 80, 80, 80, 80, 80, 80, 80. And so if you take 8 banks of 8 times 80 plus 9 times, so 8, 9, 10, 11, 12 times 80 plus the upper 16 plus 48 for the bank 12 that only has 48, that will equal 1,024 random access memory locations, 1K. And that's how your 1K is organized in your chip. Okay, so remember, the first 12 registers are going to be identical across every bank. So that goes up to so A is 10, B is 11, C is 12. No, B, 0 through B, that's 0 through 11. So after you get past B, these are different. So here you have INTCON, 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 all the way across here. You see it's the INTCON register, if I can do that. They're all mapped to the same bank. And it's true for these banks here, INTCON and everything. And you'll notice eventually, we don't have any other special function registers listed. These are just the core registers, except here there are a few. just these. And after you get past bank 8, there are no more. There might be some in the very last bank. I can't remember. Yeah, there's some tricky things in bank 31 here, but like where the shadow registers may be and some other stuff I forget. Okay. So once you get past 20 hex, then everything are starting. Once you get past 1F hex, that's the last special function register if it's there. And in some of these banks, it is. You can see it is in bank 0. But starting at 20 hex, that's where the general purpose registers are. And they have it in each register in this group of 80 is bank specific. So every one of these has a unique address that the lower 7 digits have to be in the bank. So remember, each bank is 128 locations defined by 7 bits. And then the bank address is, the bank address would be 0 in the BSR here. It'd be 00001 for bank 1, 00010 for bank 2, and so forth. 00011 for bank 3, and 00100 for bank 4, and so forth. And so all the banks have to have the right bank information in the BSR when you're using direct addressing. If you're using indirect addressing, then that's different. You use different numbers for that. And that's how you can get, let's say you needed more than 80 continuous memory locations in a matrix, you would have to use indirect addressing in that case. Okay, so notice a couple of things. In bank 0, once we get past our 12 core registers, the next 3 are called port A, B, and C. Port A, B, and C. In the next bank, they're TRIS A, B, and C. In the next bank, they're LAT A, B, and C. In the next bank, they're ANSEL A, B, and C. And the next bank, they're weak pull-up A, B, and C. So, and then this one is the logic level A, B, and C in bank 7. So you do have to sometimes access these. Now, once you get past this, most of the rest of these are all associated with the rest of the peripheral modules. The A to D converter, the touch sensing module, timer 0, timer 1, timer 2, 4, 6, and a whole bunch of other stuff. Comparator, PWM, your UART, and your I2C and your SPI, all those things have their control registers here. They look just like your random access memory locations, but they're associated with these peripheral modules that can implement various functions for you. And so, but these are bank specific, so you've got to be in the right bank for these. And then typically we'll put our variables here. Now, if you want to put them up here in Common RAM, that's fine. Sometimes that's a good strategy because then you don't have to do any bank cells. Because remember, the same 16 registers are mapped to every single bank in this upper 16. They happen to be the 16 here, but they're mapped to every bank. And so the address of those are just 070 hex to 07F hex. Those are the 12-bit addresses. And these are all 12-bit addresses. And the highest address you can see will be BFF. And that's the highest. That's the 12. That's 12. Yeah, that's 12 bits. Okay. Let's see. Can't think what else. Okay. All right, so that's how the banks are arranged, and you'll learn more about this, but most of the time you don't really have to worry about it because you just use the bank cell and it automatically points you to the right bank and everything's good. If you forget the bank cell, though, you may be, if let's say you reference LAT A or TRIS A, but you don't change the bank and you leave it set on, say, bank 0, you're actually assessing port A, or if you do, or whatever. So you do have to get the bank right. Okay. All right. I think I'm gonna. So let me go back to here. Let's see. I think I did this. All right. So the active bank is selected by writing the bank number into the bank select register using the compiler directive. Okay. Again, same thing we just talked about. The 12 core mapped across every bank, upper 16 RAM mapped across every bank, bank specific. Special function registers that control your peripheral modules and your IO ports, and general purpose RAM. Same as this RAM, except this one's just mapped these 16 are mapped to every bank. That's the only difference. Okay, we're not going to do indirect addressing, so we're not going to talk about this. Status register. So again, 3 status bits, only 2 you're really going to worry about unless you're doing binary coded decimal math. Just the Z bit and the C bit. When the Z bit is set, it means that the last operation resulted in a 0 value of the register that you're dealing with. The carry bit is set when you do a math operation or a rotate or a shift operation, and a 1 gets shifted into the carry bit or an overflow occurs. Okay. Now, so let's talk about how we do this. So I'm going to I think I'm going to switch to the document here. So let me do that. And so here's the lab. Okay, so this is lab 1. This is what you'll download from the Blackboard when you click on the PDF for lab 1. And here it is. And first it tells you what you need. You need your Viva board. You need your Snap programmer. And by the way, all the Snap. So I now have all the hardware I need. So when you come in Friday, we will give you, if you bought your Viva kit for $10, we will give you your Snap programmer, and we'll give it to you with a cable so you can plug it in. I may wait a little bit to pass out all the LCDs and the CR2102s and the analog boards, but we'll let you borrow those things for the whole course, and you'll just turn them back in at the end. But we'll make sure we pass them out before you actually need them. It'll be a couple of labs down the road before you need them, but we'll get there. Maybe 3 or 4 labs, actually. I forget. All right. So that's nice. So you'll be able to have your own Snap this Friday. And we have and also don't let's see, just for grins. Oh, here eBay. Let's look up Snap. So here they want $54. Well, that's with a little programming board. Here they want $37.97. So yeah, I don't know. And you can get them on Amazon, but so you're getting at a pretty good deal. You get the whole Viva board, you get the cases, you get the Snap, and you get the USB cable for $10. So just wanted to point out it's pretty. We're trying to make this as, oh crap, I screwed that up. I killed something. All right. Well, anyway, okay. So I want to go back to here. Okay. So anyway, so that's what you'll need. I do want you to bring in a 9-volt battery. I do have a few power supplies. So if you didn't bring your battery, we can give you one to plug in. You can also take your cable and you can modify it. What's really ideal is if you get a USB cable you don't need anymore, and cut off whatever the other end was, leave on the Type A attachment, and then I'll give you another plug and you can solder it on, and then you can plug it into your desktop or laptop, and you can power your board with the 5 volts from the USB supply. That's also a nice thing to do. And I'll give you an extra plug if you want to do that. Okay. But try and bring a battery with you so that you can power your board with the battery. And remember, do not leave your battery plugged in because it will discharge continuously whether the board's turned on or not. So you can go up to version 3.5, but don't do 5.4 because it doesn't have the assembly language. Okay, so what we're going to do is you'll see at the bottom of your Viva board, there's a little light that's at the very bottom. Let's see if I can see that on my right here, and it says "Hello World." That's an RGB LED. There's a common anode. That's important. And then there are 3 cathodes connected. One is connected to RA5, one is connected to RA2, and one is connected to RC6 right there. And they are all connected to this, that, and that little bitty current limiting resistors. Okay. So the reason that's important is because this part of the RGB LED is common to all 3 of the lights, and it's hardwired to your power supply, your 5 volts, your VDD, or your 3.3 volts, depending on how you have your jumper set. And then through the current limiting resistor, you're connected to those 3 pins. So you will not turn this light on when the pin is high, because it's high on this end, and if you make it high on this end, no current flows. So you have to ground the pin to turn on the light, which means that by default, it'll probably start off grounded. And therefore, you usually consciously have to make sure you write a 1 to turn it off so that it starts off. And RA5 is green, RA2 is blue, and RC6 is red. All right. So common anode, you can buy them with common cathodes, but with a common cathode, but that's not how this one is. It's set up with a common anode. And the roll of 3,000 RGB LEDs was kind of pricey. It was maybe, I don't know, maybe almost $300, I think, 200 and something. Okay. But then that was for 3,000, so it's not a bad deal. All right. So you should read through all this. I'm not going to read through it. The current limiting resistors prevent the more than about 20 milliamps. I think it's about, it depends on what voltage you're running at. The resistor we have on the board is 150 ohms. And so if you're running at 5 volts, you'll have a little more current going through it than if you run at 3.3 volts. And you have to do the math. You have to know how much voltage is dropped across the LED. And then you can calculate how much, then you know the rest is dropped across the resistor, then you can calculate the current. Okay, and the different colors do drop slightly different amounts, but typically the voltage drop is maybe 1.2 volts, something like that. All right, we have some registers associated with the ports. Now we're gonna talk about these in glowing detail later on. This is just to get you started. So there are four registers you really know about and need to know about, and then there's a couple others that are also relevant. The 2 others have to do with pull-ups and voltage levels for the pins, and we'll get to those eventually, but we don't need to worry about those for now. But you do need to worry about the Tris register and the Ancel register and the latch register and the port register. And again, I will cover these in much greater detail, but for now, the Tris register sets essentially effectively sets whether the pin's an input or an output. Now, what it actually does is there's a flip-flop associated with every pin, and what it essentially does is connect the output of the flip-flop to the pin. And when it's set as an input, it disconnects the flip-flop from the pin. When it's set as an output, it connects the flip-flop. So when it disconnects it, what it does, it puts it in a tri-state mode. It puts it in a high Z condition. And we'll see that when we look at the little diagram, but not today. Then we have an analog select register, and then we have a latch register, and then a port. Now, maybe I will bring that up. If we look at the data sheet and we look down here at the IO pins, chapter 12, you'll see this little diagram here. And if we blow this up, this is very key. This really is kind of what you need to know about the port. Maybe too big. Okay, that should be good. Maybe one more down. Okay. All right. Okay, so here we go. So this is the pin. This is the actual metal contact coming out of the chip. And that's what's soldered to the board. And when you plug into those female headers along each side of the CPU, you will see you have two pins that are directly connected to this IO pin you can connect to. But there are also traces underneath on the board and underneath the board that route these pins to various devices. And for RA5 pin, there's a tracing that takes it all the way to the current limiting resistor, and then all the way to the cathode for the green LED on the RGB LED. All right, so inside the chip, there are these protection diodes that are reverse biased, and they just help short out a little high voltage spikes. So they may be able to help prevent some static electricity from killing the chip. And that's why they're there. They help you if you put in too much current, they can drain some away and maybe save the chip. But anyway, that's the idea of these, or protection. And then with each pin, we have an associated flip-flop. This flip-flop is what drives the output. And here is the tris bit that controls this tri-state buffer. And it's an active low tris bit. So if the bit is 0, then this Q is connected to the pin. And if the tris bit is 1, this buffer is put in a high Z state, and this Q is no longer connected to the pin. When the board powers up, the chip powers up, there's an analog select bit associated with every pin. Some pins, it's not implemented. But if the pin has a potential analog function, then this pin will be implemented, and by default, it will be set for analog function on power up. So if you want to use the pin as a digital input, you must turn this analog function off by clearing this analog select bit to a 0. It should really have a bubble on this, but it doesn't. I don't know. It's kind of notional. This isn't really exactly what goes on. It's just a notional, so it's not really correct. But if you don't clear this, then your pin will not be connected to your data bus. So you won't be able to read the pin. Now, you have two instructions that read and write data to this port. One instruction is your latch, your LAT instruction, and the other instruction is your port instruction. The port instruction will, when you writes this flip-flop. The latch instruction, when you writes this flip-flop. But the port instruction, when you reads what's coming in on this line, reads the pin. If the analog select bit, if it has an analog select function and the analog select bit is set to a 1, then, well, and like I say, it should have a bubble here. Then this AND gate is completely deactivated and nothing gets through to the data bus. So you can't read the pin if it's left in analog mode. When you read the latch, it's gated up here. It gates Q onto the data bus here. When you read the port, it gates the IO pin here onto the data bus. But it has to be, but it's after this AND gate, which will be blocked if the analog select bit is not cleared. I know that's backwards because a 0 here would make this always a 0, and that's not how it works. So it's a little screwed up. So don't worry about that. So it's important to understand when you're wanting to use the pin as an output, you should always write the latch. Even though the port will do sort of the same thing, there's a problem because all the instructions are executed as read, modify, write instructions. So the first thing the instruction does is read, then it modifies, then it writes, and it reads and modifies and writes all of the pins in the port, which means if this pin is shorted, even though you're wanting to write a certain thing to it, if you do the port command, you'll actually read the short on the pin. And if you do the latch command, you'll read whatever you've written into the register. At least that's one of the differences. So it can screw things up in very weird circumstances. And so it's really good for you to always write the latch when you want to do an output, always read the port when you want to do an input. And don't get lazy and read and write the port when you don't want to do an output. Write the latch. Okay. So back to the data sheet. Okay, so we're just going to help you get these set up. We're going to clear the TRIS register. We're going to clear the ANSO register, and we're going to clear the latch register so that our ports are all set up to work correctly. Now, so we're going to connect up your programmer, connect up your power supply, and make sure you connect your snap correctly to the board. And I'll show you that real quickly here. Oh, shucks, I don't have one handy. Well, you just have to make sure, we'll show you in lab, make sure you connect your snap correctly. If you put it in your case, then it'll help you connect it correctly. But if you don't put it in the case, you can get it screwed up. Let's see, do I have any here? No, I don't have one handy, and I'm not going to go get one. Okay, so I'll show you that later. Okay, or maybe we may have a picture here. I don't know. Let's see. Maybe we'll come back. Okay, so we're gonna set some things up. So I'm gonna go back here, and then again we'll finish. We won't get this all done today. We're gonna finish this up on Friday. So let's see. I want to do this. Okay, so we're gonna start. The first thing we're gonna do is we're gonna start with setting up our. I think I did all this. Let's see. All right, we're gonna start. Well, here's all the instructions we're gonna use. Okay, so let me go through these. First of all, we're gonna use this bank cell, this compiler directive I talked about earlier. And what it's gonna do, it's gonna create a MOV. I'll show you the instruction it's gonna create. We'll go back down here to the instructions. 29, and we'll go back here to 100%. And it's not what I want to do. It's one of the literal instructions, and it's MOVLB. And if you look at this instruction, what it does, it takes a 5-bit literal K, and moves it into the bank select register. And so that literal will actually be stored in the instruction itself. And that literal can have a value from 0 all the way up to 31. And that's because that's the number of banks we have. All right, so that compiler directive actually makes that instruction. Okay, then we're going to use the OSCON register. The OSCON register stands for oscillator control. And if you want to learn about the internal oscillator register, then you can, let's see, reference clock mod, yeah, oscillator module. And here's a picture of it. And here's the description. There's a fairly lengthy description. There's a lot of different features. But if you go all the way to the end of that, you'll find the OSCON register here on page 70 in this one. And here's what it does. You've got a bit up here that turns on the phase lock loop if you've allowed the software to set that, that's how we're operating. But we're going to leave the phase lock loop off. You only need that if you're running at maximum frequencies, and we're going to run a little bit under maximum. We're going to run at 4 megahertz because that's just a good place to run. So we look down here. The next field is this 4-bit field that allows us to select the internal oscillator frequency. And we want 4 megahertz. And here it is, 1101. So we're going to put in a 0, 1101, and then a 0 here in this unimplemented bit. And then the bottom two, that's the clock select bits. We're going to use the internal oscillator. So that's going to be 1 with a don't care. So we'll just put 1, 0. So again, it's going to be 0, 1101, 0, 1, 0. So what that turns into, if you divide it into its hex digits, it's gonna work out to be, so 0, 1, 1, 0. So that's a 6, 1, 0, 1, 0. That's A. It's going to be 6A, or you can put in 6A is what it's going to be. And I think that's what we put in there. So we'll get around to that. So we're going to have to write 6A into the OSCON register to set the oscillator module up to run at 4 megahertz, which is what we want to do for this program. And really, we'll pretty much do that for every program. All right. Now we're going to use some actual instructions in the instruction set. And we're going to use 5 of them. So these are the only 5 you need to know for this first, really for the first couple of programs. We're going to do MOVLW, which stands for move literal to W. And what this does, I'm going to switch to this. So this MOVLW instruction, it has one operand, and that operand is a literal. It has one 8-bit value. We usually write it in hex, but you can also write it in binary. If you write it in hex, or you can write it in decimal. If you want to write it in hex, you should start out 0x and then your 2 hex digits. If you want to write it in binary, you can stand 0 lowercase b, 1, 2, 3, 4, 5, 6, 7, 8 zeros and ones. Here it's hex. And if you want to write it in decimal, you can write it up to 3 decimal digits, because remember, 8 bits unsigned goes from 0 to 255. Okay, so let's say we want to put 6 alpha in the OSCON register. Then the way we do that is very simple. First, we bank cell OSCON. Now, the compiler looks at this directive and says, okay, you want me to point the BSR to wherever OSCON, whatever bank OSCON's in. So it looks up and says, okay, OSCON's here. And I don't remember off the top of my head where OSCON is, but we can figure it out. We just have to go back to the memory. Let's see where I was at, 12, I think. No. Let's see. It's right here. Sorry. Okay, why can't I see it? It's got to be memory, data memory. Okay, I don't know. How could I do it? So we go to the banks, and let's see, OSCON's right there. So it actually has to be in bank 1. So if we really wanted to do the work, we could look it up, and we could write, instead of what the compiler is going to do, this is going to basically result in a MOVLB instruction, and it's going to be we'll just use decimal. It'll be 1. MOVLB 1. So it's going to put a 1 in the BSR. This is the actual instruction it'll create.
Dr. Morton, we can't see.
Oh, sorry. Yeah. So it'll create this. This bank cell will basically do this MOV1. So that's because that's the bank for OSCON. Now it doesn't set OSCON equal that. Okay, so continuing on then. So the first thing we do then is we bank cell OSCON. And then the next thing we do, we load up the value we want to store there in the W register using MOV literal to W, MOVLW. And we're going to put in 0x6 alpha. And then we're going to store that in OSCON. And to do that, we're going to move MOVW to file register, MOVWF, OSCON. Now, this will put the lower 7 bits of the OSCON register into the actual instruction. But the upper 5 bits, which are just going to be 00001, have to be preloaded in the BSR, but they are because we're going to do this bank cell instruction first. And that's going to take this 6 alpha, which we put into W, and it's going to dump it into OSCON. And that's going to configure the OSCON register to run our chip at 4 megahertz. Now, that's conditioned on having done the configuration registers correctly. And let's see if we have time to do that. Yeah, I think maybe so. So let me go back here. Let's slide this down. And wait. Okay, so back here. So we're going to do, so the first thing we're going to do is we're going to set up these configuration registers. I'll go through, we still have to talk about, so we've talked about the bank cell, we've talked about the OSCON register, we've talked about MOVLW and MOVWF, but we haven't talked about clearF, bitsetf, and decrement F skip on 0, which we will get around to, but probably do that on Thursday. All right, so when we actually want to create a project, I'll walk you through that real quick, and then I'll do the configuration words, and we'll probably quit with that. Okay, so here's my program. Now I'm gonna do this. Let's see. Yeah, here it is. So I think I'll just start again. Yeah, we'll just start again. Okay, so what I want to do a new project. So I just click on File, New Project. And then I click on Microchip Embedded, Standalone. I've put the 32-bit stuff in, so I could have clicked on that for some of the more fancy processors, but we're going to use an 8-bit, so we're just going to click here. Harmony is it's kind of does a lot of the work for you, but only for the 32 bits. All right. And then I have to put in our chip, PIC 16F1829. I can also, well, it totally screwed up. I don't know why I didn't overwrite that. And then if I get here, I can scroll down and find 29. Notice there is a PIC 16F1829 LIN. That's a chip that's specifically for the automobile market. And we don't want to use that one. It's got some extra modules in it. It's a different chip. So we want to do the 1829. Then we click next. This is a special header thing. I'll explain that later, but we're not going to use that. So we're just going to hit none. And then here's our programmer. And you're going to click on snap, and it should show a serial number. I'm going to use my ICD4, and it shows my serial number. So it means it is, I've plugged it in, and the integrated development environment has recognized it, and it's talking to it correctly because I can see the serial number. You'll see that if I plugged in the snap, you'd see the same thing. You'd see the serial number for your snap. And you can actually give this a name like John Snap if you want or whatever. All right, so I'm going to click on this. And then here's where you get to pick the MPASM. This selection's gone when you get to 5.4. So that's why we don't use 5.4. So we click this. When we get ready to code, we're going to use XC8 1.45. That would select for a C program. But now we're going to do this. Okay, Now we're going to give our project a name. So we'll call it test blink 1 or something. Who knows? Test blink 1. Okay. And then we'll do finish, and it'll create a directory, and it doesn't put much in it initially. Here's our program. Now we want this program to be the main program. So when we do all these functions up here, we're actually affecting this one and not one of these other ones. So to do that, we make sure it's set as main. In this case, it says unset as main. So we know that it must be set as main. Otherwise, it wouldn't say unset. It would say set as main. Like if I click on one of these up here, it says set as main because it's not the main one. So as long as it's the main program, it'll be highlighted. And when we right click, it will say unset as main. So we know that's good. You can also just keep only one program active in here. It's probably smart to do that. So the first thing we want to do is we want to set up a source file. So we click on this, there are no source files, and we hit new, and this is all in the instructions. Pick underscore 8-bit simple.asm. If we wanted to do a C, we would just hit main C. But we want a simple. There's also a general assembly file, but we want to use a simple one. So we click on this, we give it a name, and then boom, here's what it creates. It says to do, insert configuration code here using the config bits generator. And here, to do, if you want to use interrupts, put them here. And then here, it's a loop forever. This is where we want to put our main code. All right, so now we're going to do the configuration bits, and I'm going to clear this and start over. So if you go under Window and down to Target Memory Views and down to, well, you don't actually have to do this. You just click on Configuration Bits, and here they are. And so we can go down through here, and we're going to set all these the way we want them. Now, they're not set correctly by default. The first one here, external crystal high power. So we're not going to do that. We're going to use an internal oscillator. So we want to go down to INT-OSC, internal oscillator. Watchdog timer, we don't want it enabled. We want it off. Power up. Anyway, it basically tells what it does. And this gives you a little more information on it. Okay, but power up timer enable. We don't care about that because we're going to use the internal oscillator, so we'll leave it off. Master clear enable. We want that on. Code protect. We want that off. Code protect data. We want that off. Those are set up in case you want to keep somebody from reverse engineering your product. Brownout enable. This is if you're running a battery operated device. You can leave this on or off. It doesn't really matter. But I usually turn it off unless you're actually doing a battery operated device. Clock out enable. This is so we can see the clock. I'll enable that and show you the clock maybe on Thursday even. But for now, we definitely want that off because it takes up a pin. Input internal external clock switchover enable. We want that off because we don't have an external clock. Fail-safe clock monitor. We don't have an external clock, so we're going to leave that off. Watchdog self-write timer, self-write protection. We want that off. Phase lock loop. We want that off because we're not going to use a phase lock loop. Stack overflow, underflow, reset enable. You can leave that on or off. It doesn't really matter. That's just if you do more than 16 levels of 16 pushes on your hardware stack. And then this will reset the chip if you leave that on. If you don't leave it on, the chip will just keep trying to run, but it will be screwed up because you're going to not ever get back to where you started. Here's your brownout voltage selection. You can select the low or high voltage. And finally, low voltage programming. That must be left on. It is on by default, so don't turn it off. Now we hit generate source code, and boom, here we have what we need to paste into our program. Now, what I've done in my program, I created another file. I went up here under the header and I right-clicked here, new file. Let's see, I don't think that it did. I do that right. Yeah, so I run a right-click. Yeah, here, new. I want to hit other because it doesn't come up in the list. I want to click on assembler. I want to click on dot include and then next. And then I'm going to give it a name and I'm going to call this config. And I don't know why that came up. Oh my God. I want to give it a name config, and it's going to have an extent of .inc, and it'll do that automatically. And so I hit finish, and now it gives me a blank file, and I'm going to take this that I've copied down here. I'm going to copy it, and I'm going to post it in here. Post it all the way at the top. And now I've made this little file, and I'm going to add 2 more lines to it. Real quick here. I probably won't talk about these too much. Let me just do them. Let's see. I did this up here. I think I have it right here. I'm going to add one more line. I'm going to add this list line. Mostly, you probably don't really have to have it, but I kind of like to do it. All right. And all this does is basically it tells the lister that it's a 16F1829, and it sets your radix for decimal. So if you don't specify, it'll assume decimal, which I think is by default. But it's nice to have that in case you change it. And then basically once you've created this file, you can store it someplace and you can load it in every time you do it. You can just, you can create it here and paste this information in, and you'll always be set correctly. And what's nice then is you don't have to clutter up your main listing. So in your main listing, you can just do include quote, double quote, config.inc, double quote. And as long as you've put it up here in your header, then everything will be happy and this will work great. And then it just makes it a little faster to put this in, and that way you won't make a mistake and accidentally erase something in it. But you don't have to. If you want to just take this here, copy it as is, and copy this and just paste it in here instead, you can do that. That's fine. That'll work too. But oh, somehow we missed it. So then we actually should have done that. You should have 2 configuration lines: configuration word 1, configuration word 2. And these are all your selections just laid out here. Okay, I think I'm going to stop there. We'll pick up then, we'll pick up on Thursday and finish this up. We'll get into the more enjoyable part where we actually do something with our chip. All right, any quick questions?
No quick questions.
Okay, long question. We can let everybody go then if they want. And then I'll hang around a minute, Daniel, and you can ask one.
Okay, thank you.
Thank you, Professor.
All right. Okay, anybody had a long question can stick around. Go ahead, Daniel.
So we should be working on the homework, correct? Is that, because
Yeah.
I know you mentioned it yet in the lectures.
Yeah, so I'll probably say, let's see, let me pull up the syllabus then. I think it's here. So homework 1 is due on the 2nd. So I'll say some, so it's due on Thursday. I'll say something about it. I'll look at it Thursday and talk about it briefly.
Okay, because most of my questions come from that and just trying to understand exactly what we're doing with the IPC and how it all functions.
Yeah, okay. Yeah, okay, remind me when we get started on Thursday, and I'll cover that. I'll cover that at the beginning. I'll just say a few things and hopefully you should be good. It should be pretty straightforward.
Do you mind if I ask a couple of follow-up questions like to that, just to make sure like I'm understanding the general concept? Okay.
Yeah, no, go ahead.
Specifically with the programmer's model.
Okay, let me pull that up. Then it's should be here. And
And probably some of the architecture too. I just want to make sure like understanding how the microchip is working and what it's doing.
Okay,
Okay, so the program memory, that's where all the functions are stored, and that's what we reference when we're trying to program, correct?
so the program memory is where all where the program instructions are stored. So when you write code, it gets assembled. If you write it in C, it gets compiled and then it gets assembled. If you write an assembler, it just gets assembled into machine and it gets put in that part of the memory. And you can actually go into the integrated development environment. You can pull up your window and you can put up target memory views, program memory, and then you can just scroll down through the memory and look at all the instructions.
Okay, so
In this
program
case-
memory is what we're writing into the chip.
That's
to make
right.
it what we want.
That's
And
right.
the CPU interprets it.
Yeah, yeah, you can think of it that way. It's more the case that the instructions tell the CPU what to do.
Okay. Okay, so then from there, we have the data memory, the EROM registers, and the oscillator.
Right. So you can you can do the same thing here. Target memory views. You can look at special function registers. You can look at you can look at file registers, which is basically the data memory. Here's the data memory.
You don't have your screen showing.
Oh, sorry. I don't know when you can see. So here's the data memory. So what you do is you go into Windows or Window, target memory views. Here's the program memory. There's nothing in it. So every location, remember, every location is 14 bits. They're all set to 3FFF because it's a ROM, and it's always, all the bits are set by default. We clear them to program it. And if we scroll that, since we have what do we have, 8K of program memory, we'll go all the way up to 8K of instructions here. If you want to look at the special function registers, then you go target memory views, special function registers, and here's all our registers. The core registers will always be here, and then so there's the BSR. So here's this INDF0 and INDF1 are how we refer to the indirect registers. These are actually not locations, but they will show you they'll show you the, well, I don't know. Anyway, there's the program counter low, there's the status register, there's the file select register 0, high and low. And then there's the low by itself, there's the high by itself. And then there's the two registers together, the low by itself, the high by itself, the bank select register right there, the W register right there, the program counter latch high there, and the incon register there. Those are the 12, those are the core registers. In bank 1, next comes port A, port B, port C, and a bunch of other stuff. And then in the next bank, TRIS A, B, and C, and a bunch of other stuff, the peripheral interrupt registers. And the next bank, latch A, B, and C, and a bunch of other stuff. This is all of the registers that control all of the special, of all the modules and all the ports and all the special functions. This is it, the entire bunch of them.
Okay, so it's the CPU finds the register using the BSL, using the upper 5 bits, right?
That's right. Lower 7 bits are so the name, each of these names refers to a 12-bit address. And when we want to actually get at that address, unless we're using indirect addressing, but if we're using direct addressing, which is what we're going to use, we have to make sure that the upper 5 bits are in the BSR, and then we will automatically put the lower 7 bits into the instruction when we put the variable name in the instruction. So when we put OSCON in our instruction for MOVWF, it takes the lower 7 bits of OSCON's address, which if we look at OSCON, it's in the next bank here, right there. So its address is in hex. Well, no, I guess that's in yeah, that is hex. So its address in hex is 099. So if you think about that, you take, so if we write that out, right? If we write that address out, 099 then would be in hex, so 0x99, that's 10011001. So the lower 7 bits are 0011001, and the upper 5 bits are 0001. So this goes in the BSR, and this goes in the instruction. And in the actual instruction, you would have 1, 9. And in the BSR, you would have 1. And that would point you then to the OSCON register.
Okay, so the CPU is using the bank select to
Yep.
determine where and what.
It concatenates the contents of the BSR with the lower 7 bits of the instruction address and of the operand in the instructions, which its lower 7 bits are there. So it takes that lower 7 bits, concatenates the upper 5 bits, generates a 12-bit address, and goes out and fetches, either writes to or reads from that 12-bit, or does something to and puts the result in that 12-bit location.
Okay, so the upper 5 is like the calling the name of the register, and then the lower 7 is here's what you're doing. Basically.
No. So let's if you just look at the instructions themselves, if we go into the register, so let's actually look at the instruction. Go down to chapter 29. That's how I'm not there. Okay, so here was that question, MOVWF, where we're going to move 6 alpha that we stored in the W register into the OSCON. So notice the upper bits are, so this tells you exactly what gets written. And what gets written here is 00, the 14 bits, 00, 00001, and then FFF, FFFF. Okay, so those F's stand for the file register address. And if you count it out, that's 7 bits. So that's the lower 7 bits of the address. So that lower 7 bits of the address is right there. And in our case, we just looked at it. We saw that lower 7 bits was 0011001. That happens to be the correct address for OSCON. And the bank is bank 1. So the BSR must hold a 1, and the lower 7 bits must be this.
Okay.
And then if all that's done correctly, then this MOVWF instruction will write the contents of W into OSCON.
Okay, wait. So the upper 5 determine the bank.
That's right, and it's located in the BSR.
That gets us into the right array. If I'm thinking about like 2-dimensional arrays.
No,
Way
well,
of thinking of it.
just think about it as 31 different drawers. That gets it in the right drawer. And then each drawer has 128 slots.
Okay, so then the lower 7 are, we want the lower 7 to go somewhere, and that's why we selected the move function, right?
Right. Well,
Okay.
so remember, the lower 7 bits are an address. So remember, every time we're dealing with doing something, with a computer program, we're dealing with addresses and data. And you always have to keep in your mind clear what's address and what's data. Now, the problem is that, and I have to go in just a minute. I got another meeting that I'm actually due at 1 minute.
Okay.
But the address is not the data in most cases. In indirect addressing, we actually turn the address into data. That's why it's a little confusing. But for the most part, the address and the data are always separate if we do direct addressing. So the lower 7 bits have nothing to do with the data. They're only the lower 7 bits of the address. The BSR has nothing to do with the data. It's only the upper 5 bits of the address. And the data then happens to be what's in the W register. In this case, we're taking the data from the W register and writing it to this OSCON location, which is a file register. And that file register then configures our oscillator module to run at 4 megahertz for the internal oscillator. And we also have to have the configuration bits set correctly for that to work right, because we have to set the configuration bits up to set us for internal oscillator.
Okay, I think that gets me in the general ballpark of understanding things.
Yeah, there's a lot. And there's a lot that sort of, it's like swallowing the watermelon whole, but that's kind of what you have to do. And then eventually, then you can go back and we'll fine tune all the little bytes and it'll all make total sense to you. But there's a lot of the big picture you have to kind of get first.
Okay, so big picture, we have a programmer writing into the chip. The CPU is distributing that to where it needs to go using the BSR and the addresses.
Yeah, yeah. So we'll I think it'll be a little more clear on Thursday, but we're just taking baby steps. All right, I gotta go.
Thank you. Bye.